So on Friday, we got deep into perimeter and area and using our Pythagorean theorem, our a squared plus b squared equals c squared, to find missing pieces to help us with that. So if I were to ask you to simply find the perimeter of several shapes, we're going to start off with, we're going to start off with my handwriting. Something simple like this. Oh, let's make this 11 inches here. We'll make this 60 inches. Obviously not drawn to scale. 100 inches. Work on finding the perimeter of that while I put up a couple of more examples. Okay, so for these first three, we're finding perimeter. Perimeter is just the distance around. So we'd have to add up for number one, the four sides. So we have 100 here. Oops. Come on. 100 inches here and 100 inches here. We need to know the length of those sides. Well, this is simply a right triangle here. It's 11 and 60. Both of those are the legs. So in order to, in order to find that missing side, we would add this, we'd square them and add them together. It's going to be the square root of 11 squared plus 60 squared. So second square root, 11 squared plus 60 squared, gives us 61. So this distance here is 61 inches. So we have to add 61 inches and another 61 inches here, giving us a total of 322 inches as the perimeter for number one. How many of you had 322 for number one? Okay. Perfect. Number two, we have to find the missing side again here. This is a right triangle, but the missing side is one of the legs, which means we have to start with the hypotenuse and subtract So it'll be the square root of 65 squared minus 16 squared. Second square root, 65 squared minus 16 squared, gives us 63. So this is 63 feet. So giving us a perimeter of 63 feet plus 65 feet plus 16 feet. What is that, 144 feet, I believe, of total perimeter. How many have 144 for number 2? Perfect. Now, number 3, the perimeter of that is just the circumference of the circle. What's the formula for circumference? Pi times what? Careful. Pi times diameter, or 2 times pi times radius, right? So for this circle, what is the diameter? 16 inches. Good. So if I use 3.14 for pi, 3.14 times 16 is going to give us 50.24 inches of perimeter. Any questions on any of those first 3? Next, we're going to ask you to find the area. I'm going to put 4 of these up here. This first one, we're going to go 9 inches, 19 inches, and 16 inches. Find the area of that triangle. Number 2, oops, sorry, get back up here. There it goes. And number 3, there, we'll work on those 4. We'll go over those in just a couple minutes. Bless you. Well, let's see how you're doing on these. So number 1 is probably the most difficult of these 4 because it's a triangle with no right angle given. And of course, to find the area of that, we have to use Hero's formula. And to find Hero's formula, we start with the perimeter. So we're just going to add up the sides. So 19 plus 9 is 28, plus 16 is 44 inches. What's our next step then in Hero's formula? Semi-perimeter, right? Half of the perimeter. So 44 inches divided by 2 is 22 inches. And then it's the ugly formula. Semi-perimeter times the semi-perimeter minus, we'll go minus 19, times the semi-perimeter minus 16, times the semi-perimeter minus 9. We subtract each of the sides from the semi-perimeter in that formula, in that square root. So second square root, 22, times 22 minus 19 is 3, 22 minus 16 is 6, and 22 minus 9 is 13, 71.75. Those are in inches, so this is square inches, is the area of that. Did anybody get that one? Okay, well, I'll give you a half a minute or so to get that down so you have it in your notes. Because in the quiz we're doing at the end of class today, there is a Hero's formula problem. So this formula here is area equals S times S minus A times S minus B times S minus C. Okay, number 2. To find number 2, the area number 2, we need this dimension. Remember, for area, it has to be 2 dimensions that are perpendicular to each other or make a right angle with each other. So to find that dimension, what do we do? There you go. 25 squared minus 10 squared, and then square root it. We get that distance is... It does not come out perfect, does it? 22.91. So then the area is at 22.91 feet times 30 feet, giving us... Do I have to divide by 2 here? No, that makes a full rectangle. It's not a triangle. So 687.39 square feet. Number 3. Again, we need to find this missing side, and again, it's going to be that reverse formula. What did you guys get for that missing side? What's it come out to be? 9. Perfect. So then to find the area, what do we multiply together?
40 times 9 divided by 2.
Perfect. 40 times 9 divided by 2, giving me 180 square inches. Number 4. Area of a circle. What's the formula for the area of a circle? Pi times what? Radius squared. So here, what's our radius? Four. So pi times 4 squared gives us 50.24 square feet. Perfect. So since we ended on a circle problem there, I want to talk a little bit more about finding areas and perimeters of circles. In fact, what I want to focus on is partial circles. So if I have a circle, hey, that one almost looks round. I shouldn't sound so shocked. If I have a circle and I want to just find a piece of that circle, if we had a half circle, we divided by 2. If we had a quarter circle, we divided the whole area by 4. We're going to look at a circle and we're going to define the size of the circle by an angle. So that symbol that I put in there is the angle theta. And it's a variable that tends to get used just for any unknown angle. And this piece here, that looks like a pi wedge basically, is called a sector of a circle. Or just a sector. To find the area of a sector, we start out just like we did with a quarter circle or a half circle. We find the area of the full circle, and then we're going to multiply by that angle over 360. Now this is called a central angle because it has to be at the center of the circle. But it also, because it's at the center of a circle, it defines a fraction of a circle. If we look up at examples we've done before, when we did a half circle, this angle would have been 180 degrees. So that would have been 180 over 360, which reduces to 1/2. 1/2 the area of the full circle. For a quarter circle, this would have been 90 degrees. Well, that would have been then 90 over 360, or 1/4. 1/4 of the area of the whole circle. So now using this formula, this idea, we can look at what if this angle is 110 degrees and the radius here is 8 inches. To find the area of that sector, we're going to find the area of the whole circle. So the area of the whole circle will be pi times what here? Radius squared. So here that would be 8. Pi times 8 squared is what? 200.96. This helps if I get all my zeros in there. Square inches. So then to find the area of the sector, We take the area of that whole circle, 200.96 square inches, times what? 110 over 360. Because that central angle of 110 degrees defines the fraction of the whole circle. So 200.96 times 110 divided by 360. Gives us 61.40 square inches is the area of that sector. Well, sometimes we're not just looking for the area of part of a circle. We're looking for the circumference or the perimeter of part of a circle. So if I have, again, my central angle of theta here, and what I'm trying to find is this piece here, the portion of the circumference that's cut by that angle. That piece, by the way, is called an arc. It is sometimes defined as just in degrees, which we'll talk about later on in the class of defining an arc by its degrees. But we want to find the actual length of it compared to the radius. And so that arc length is simply the whole circumference times theta over 360 degrees again. So it's the same correction, basically, as we use for the area of a sector. So if this is 80 degrees, and this is 5 feet of a radius, I'm going to start by finding the circumference of the whole circle, which is going to be pi times what here? Pi times diameter, and the diameter would be 10. There we go. So 31.4 feet is that whole circumference. So then the arc length is the 31.4 feet times what? 80 divided by 360. Perfect. Giving us 6.98 feet of arc length. So that just gives us this piece here. So pretend that looks like a piece of a circle. Let's do 24 feet radius. Let's do 76 degree central angle. We're going to start out by finding the area of that sector. So the first step in finding the area of the sector is finding the area of the whole circle, which is going to be pi times what? Radius squared. So that'll be 24 squared. $1,808.64. That's in feet, so this is square feet. So then the area of the sector is that 1,808.64 square feet times what? 76 divided by 360. Good. So we got 381.82 square feet. So now the perimeter is slightly trickier. We're going to start out by finding the circumference of the whole circle, which is going to be pi times, not 24, but 24 is the radius. Circumference is pi times diameter. So pi times 48. So 150.72 feet. So then to find the arc length, we take that 150.72 feet and we multiply by what? $76 over 360. Good. So that gives us 31.82 feet. But that's not our whole answer yet. All that gives us is this arc length here. We asked for the full perimeter of that figure. What two sides do we still need? Well, we need 24 and 24. So plus 24 feet for one radius, plus another 24 feet for the other radius, which gives us 79.82 feet of perimeter. Any questions there? Okay. So the next thing we want to look at is we want to look at some more complicated areas. And the area that I'm looking at, to define the area I'm looking at, I need to define a structure called a chord. A chord is just what I drew here. It is any line segment that has its endpoints on the circle. So this is a chord. Technically, a diameter of a circle is a chord. A diameter is just a chord that happens to go through the center of the circle. But anyway, what we're going to try to find now is the area of this piece here. And this little piece, this sliver of the circle out here that is cut off by a chord, is called a segment of a circle. Well, without calculus, there is no way to calculate it directly. So we have to find it by finding the area of two related pieces. Those two related pieces, well, one is going to be the sector. The sector is going to go all the way out there. The second related piece is going to be this triangle here. And of course, we're going to subtract those to get the area of that segment. So what we're going to do is we're going to look at some special cases here that make it easier on us. We don't know trig, and we're not going to get into trigonometry in this course. So some of the more complex examples would involve trigonometry. I'm not going to do that to you here. But we're going to look at an example like this, where if I tell you that this is 15 inches here. And, of course, the other radius is 15 inches. And that the chord is 15 inches. And we're trying to find this area of the segment out here. What can you tell me about this angle here? Well, the triangle here has all three sides the same, which means the angles of that triangle must be how big? 60 degrees. So to find the sector area, we start out by finding the area of the whole circle. Pi times 15 squared. Which gives us 706.5 square inches. From there, how do we find the area of the sector? What do we do to that to find the area of the sector? Times 60 over 360. Perfect. 60 over 360. What does that give us? 117.75? Yeah. So that is the area of our sector. We need to remember that. Next, we need to find the area of that triangle. Well, because this is an equilateral triangle, there are no right angles in it. We're going to start off by finding the perimeter of that triangle, which is just 15 inches plus 15 inches plus 15 inches, giving us how much? 45 inches. And then we're going to find the semi-perimeter, which will be found by 45. What do we do to the 45? Divided by 2. Good. So we get 22.5 inches is the semi-perimeter. So the area will be the square root of 22.5 times 22.5 minus 15 times 22.5 minus 15 times 22.5 minus 15. I get 97.43. Square inches is the area of the triangle. By the way, if you're watching, I did a shortcut there since I knew all three of these were going to be the same. They're all going to be 7.5. I just put it in as 7.5 to the power of 3, so I didn't have to type it in 3 times. It saves a tremendous amount of work on the calculator if you subtract these in your head or just subtract them on paper before you punch them in. Okay, so anyway, to get the area of our segment then, we're simply going to take our sector area, 117.75, minus the area of our triangle, 97.43, And we get 20.32 square inches is the area of that segment. Now I realize that was loads of fun. Not a calculation you probably want to do every day. It will appear on a quiz at some point, but I'll try to be gentle with you about it. Let's do another example similar to that. In fact, I'm going to try to be really nice to you in this example. And I'm going to have you try this on your own. So if this is a radius of 8 feet, find the area of this segment out here. I'll give you about 2 minutes and then we'll go over that. Let's take a look here. So we're going to find the area of the sector first. And this one would be a lot simpler than we're going to make it if you just divide the whole circle by 4. But we're going to go through the whole process. The area of the whole circle would be pi times what? Eight squared. Good. Which is going to give us 200.96 square feet. So then the area of the sector is the 200.96 square feet times what? 90 divided by 360. So we get 50.24 square feet. So there's the area of our sector. The area of our triangle is actually pretty simple. How do I find the area of my triangle? Oops, you're thinking area of a circle. For the triangle. 8 feet times 8 feet divided by 2. There we go. So that's going to be 32 square feet. I subtract those to get 18.24 square feet is the area of the segment. So that piece right there. What do you think? Not so bad? That's one of those that's more difficult to remember the process than it is to actually do it, at least on the examples I'm going to be giving you to do in the next couple of weeks. So we've talked about chords. I want to talk a little bit more about chords here. In fact, I want to talk about intersecting chords. So if I have a chord like that, and then another chord that intersects it like this. Let's say this chord here is split into pieces of 4 inches and 9 inches. The other chord can, the size of one of the pieces of the other chord can then be predicted if I know one of the other piece, basically. If I know this is 3 inches. Now first, looking at this picture, could I reasonably expect those two chords to be the same length? No. No. In a circle, I can have chords of all different lengths, right? I can have a chord here. This chord's going to be longer. Of course, the longest possible chord would be the diameter of the circle, right? So the length of the chord can be anywhere from the length of the diameter down to nothing. To find the length of this missing piece here, which we're going to call x, we use a property of circles that within the same circle, intersecting chords cut themselves into pieces that have a common product. Common product means if I multiply the length of the pieces together, it'll be the same. So this chord is cut into pieces of 4 inches and 9 inches. So that'd be 4 times 9. And that has to equal the pieces of the other chord. This chord has 3 inches and x inches. So that's 3 times x. Well, what is 4 times 9? 36. So what does x have to be so that 3 times x equals 36? 12. Very good. So this has to be 12 inches. The shortcut formula for this is that missing piece, if I have my chords here, let's put my chords in here. If I call these pieces A, B, D, and X, is that the length of X has to be A times B divided by D. Oops, there goes another page. Oh, so let's say that I have lengths. Let's just go 16 inches and 16 inches here. And we'll call this piece, well, 8 inches. To find X, well, the length of X, what two pieces are going to get multiplied together here? Perfect. We multiply the pieces that are in the same chord. Now we're going to divide by 8. So 16 times 16 divided by 8 tells us that X has to be 32 inches. So if we have two intersecting chords, if we know 3 of the pieces, we can find the 4th piece. That is actually a big rule in construction, combined with some of the other rules we're going to see here in just a second. It's a calculation that gets done a lot. So the next big rule, it's actually like 3 big rules all combined into one, is if I have a chord and then either the radius of a circle or a diameter of a circle, it really doesn't matter which. If the radius of the circle cuts the chord at a right angle. So it hits it perpendicular. That means it cuts the chord in half. Those two pieces will be equal. The opposite is also true. If the radius happens to cut the chord in half, it has to intersect it at a right angle. So what that allows us to do then is it allows us to look at a circle like this. Let's say this is the center of the circle, so we know that that's actually a diameter of a circle. If I know that this hits at a right angle, and if I am told that this whole length here of this chord is, well, let's call that 48 inches. And let's call this length here 16 inches. I can find this length here of x. The reason I can find it is, well, what do these two pieces both have to be now? $24 each, perfect. Since we know this hits at a right angle, we know it cuts that chord in half because it's a diameter or a radius of the circle. So then to find x, the length of x is going to be 24 times 24 divided by 16, which is going to give us that x is what? Was it 36 inches? I gotta double check that one. 36, perfect. So that's 36 inches, which tells us the diameter of our circle has to be 36 plus 16, or 52 inches, which of course would make the radius half of 52, or 26 inches. So I made a big deal of this a few minutes ago. Why is this so important in construction? Well, because in construction, one common structure is an arch. So if I have a doorway, and let's say this doorway, it's an entryway, a passageway between a living room and a dining room. And let's say that this is 64 inches across. And they want us to create an arch over the top of that doorway. Rather than having it cut off flat, they want there to be an arch there. Let's make this height here of the arch above horizontal. We're going to make that height 16 inches at the center. So what that means is, and my circle is going to be kind of squashed here, but that's okay. We use our imagination. We can find the length of this piece here, x, because this piece is going to be how long here? 32. So that means this piece is also 32. So x is going to be found by doing what? 32 times 32 divided by 16, or 64 inches. Which means the diameter of our circle is 64 inches plus 16 inches, or 80 inches. So the radius of the circle is half of 80, or 40 inches. Why is that important? Well, because the way we would lay this out to make that arch is we would take a piece of plywood or OSB or whatever, and we would lay it on the ground, and we would find the center of that circle. We would take that 40-inch radius. In other words, we'd just take a 40-inch piece of string. We'd hold it at that center of the circle here, and we'd stretch it out, and then we'd just rotate it to cut that arch. And now we would use that template then to make the top of our doorway. Okay, you guys have had enough for the day, so 2 things I want you guys to work on. First, you have that quiz that I gave you last Friday. It's the quiz areas, and it says quiz on areas and surface areas. It's areas and perimeters is what it is. Then the second is in that packet, that big packet we gave you last week. It's page 165 through 168. Has again, the gray boxes with problems in it. On Friday, we will take some time to go through some of those problems, just to make sure you guys are on track with them. With that, I am going to shut down the recording here and give you guys some work time. You guys can have the last 14 minutes here to work.